All right. So Monday we talked about these substitution reactions. And when we stopped, we were talking about the difference between SN1 and SN2. So this idea that either the substitution can proceed by by the leaving group coming off and then the nucleophile coming in, or you can have SN2 where it all happens at the same time. And we were just kind of in the middle of a way to decide of some of the things that we look at to decide that. So just to review, the first things we looked at were 1, carbocation stability. A more stable carbocation is going to favor SN1. 2, steric hindrance. Crowded substrates favor SN1 because the nucleophile can't get in there, doesn't have space to get in there. Third, we looked at the leaving group. The leaving group is going to affect both of them. So that's not generally a good driver of one versus the other. And then when we stopped, we were going to talk about solvents. The solvent that you use can greatly affect which mechanism is favored, either SN1 or SN2. So we looked at 2 classifications of solvents: protic solvents that contain OH, actually NH also, and aprotic solvents that don't contain OH. And we said these are all polar solvents. You need polar solvents to do these reactions. But which polar solvents you use have a big influence on the reaction, and here is how. So rather than try to draw this, I'm going to grab a picture again from the book. So this is page, where's that picture? 204. Here we are. And we're going to look at how solvents stabilize dissolved substrates. And we're going to look at the difference between how a protic solvent stabilizes a dissolved substrate and how an aprotic solvent stabilizes a dissolved substrate. So let me grab these pictures and then we'll talk about it. All right. So first let's take a look at the protic solvent, because that's kind of what you're used to from your previous chemistry classes when you talked about how things are solvated. And let me use some color here to show you what we're really looking at. So whenever you're dissolving an ionic species, like when you talked about sodium chloride being dissolved in water in Gen Chem, this is kind of the picture that we always use. The ions go in the solvent, and the solvent kind of lines up so that the positive parts of the solvent go with the negative ion, and the negative parts of the solvent go with the positive ion, and they all kind of form this like network of solvation. Does something like that look familiar to you? Have you heard of that before? If not, just let's review that then. Water makes a hydrogen bonded network through its intermolecular forces, and in order for something to dissolve in water, it has to interrupt that network. And the things best suited for that are charged particles, negative and positive ions, because they can get in that network and form their own interactions with water, which are actually stronger than the hydrogen bonds. So the interaction of an ion with water is going to be stronger than the hydrogen bond, and that's why we have usually that in entropy is why solvation is usually favorable energetically. So that's our typical thing, and that's what's happening in an SN1 reaction also. When we're forming a carbocation, we can use the solvent to help stabilize that cation by solvating it. And at the same time, that solvent is solvating the anion, which we're calling the nucleophile. So our nucleophiles are also well solvated in solution. If we compare that then to an aprotic solvent, like acetone, the negative side, this is actually a typo there, that's supposed to be a minus. The negative side of the molecule is the only one that can really line up with, the only one that's really exposed, because the dipole is sort of inside the molecule. So the negative oxygen can form a solvation sphere around the carbocation, but that leaves the negative anion, the nucleophile, without any kind of stabilizing solvation sphere. And this is a little bit of an exaggeration, because if there were truly no solvation of the anion, it wouldn't dissolve at all, and it does dissolve. So their picture is a little bit exaggerated, but the idea is that a nucleophile is much, much stronger in an aprotic solvent because it doesn't have all these hydrogens to help stabilize it and surround it. So if you kind of look at this, I'll just highlight that it's sort of naked is the word that the book uses. The solvent can solvate the cation but not solvate the anion, so if that means that it's unlikely to detach like that. You're unlikely to form a carbocation in these solutions. So that tells us that if we go back to our solvent list, our protic solvents are going to favor SN1, and our aprotic solvents are generally going to favor SN2 for those reasons. So what you should personally know about these is first to be able to identify protic versus aprotic solvents, to recognize or remember which mechanism is favored in those, but then perhaps most importantly to understand the reasons behind them, so that if you forget or you get mixed up in your head with which one's which, you can still work it out logically. If you know what's going on, if you think about the effects, then you can figure out logically what's going to cause what, and you don't have to just remember this does this and this does this. So any questions about those effects? All right, so let's look at some examples now where we look at some particular reactions and try to decide what the product's going to be based on these factors. Let's see if I can find it.
Taking into account all four of the
Yeah.
factors,
Mm-hmm.
which one happens more often, though, SN2 or SN1?
Well,
Because I'm thinking of that question that you just had with if the products are typically hydrophilic or not.
so it's meant to, it's not, I don't know which happens more. It really depends on the conditions, and because we're, as experimenters, we're the ones setting up the conditions, we often are going to want to control that. So usually the way that I would think about this is generally SN2 is the more desired outcome. SN1 is something that you have to watch out for, because usually you want SN2 because it's more carefully controlled, but some substrates aren't going to do SN2, some solvent conditions aren't going to do SN2, and so we have to kind of be careful about those if we want to preserve our stereoselectivity or whatever, stereospecificity. If we don't care, then we don't care, but it really depends on each individual reaction. So if we look at something like this, all right, and we want to predict the product. Well, we want to do two things. We want to predict the product, and we want to identify the mechanism. So first, we're going to figure out the product, and second, we're going to give the mechanism. So to figure out the product, we look at the substrate, we look at the nucleophile, we figure, okay, our leaving group is going to be iodide. Everybody guess that here? Okay. And what's the nucleophile? It's going to be methanol. And what's the solvent here? Also methanol, because nothing else is shown. Nothing else is given. So what we're doing here is we're just taking some iodocyclopentane, throwing it in some methanol, seeing what happens. Okay. So it's what? It is. So in this case, our product is the substitution product. And generally, like with the quiz, we can get out of that general chemistry mode of always keeping track of all of our byproducts and balancing everything. And we can just say, okay, we're starting with the substrate, we're doing a substitution, we're making this product. Everything else is just going to get washed away. But that's our product. Now, do we have to know the mechanism to find that product? Or is it going to be the same whether it's SN1 or SN2? It's going to be the same. The only thing that would ever be different about an SN1 and an SN2 product, well, that's not true. Not the only thing. But generally, the difference between an SN1 and an SN2 product is the stereochemistry. That stereochemistry is maintained with the inversion of configuration in SN2, and it's lost in SN1 because of the carbocation. All right, so looking at this then, let's say that it was like an exam question, and I said, draw the product and draw the mechanism of this reaction. So the product, all we need to know is the leaving group and the nucleophile, and then we just switch them. But the mechanism, we need to know a little bit more, because we have to figure out, are we going to draw an SN1 mechanism or an SN2 mechanism? So let's think about our 4 categories. First, the substrate. Is this something that can make a carbocation or not? Well, what do you think? What types of carbocations can we usually make? Or what types of substrates absolutely will not make carbocations? It's the primary substrate, right? Where the leaving group is on a primary carbon. That's not going to leave in form of primary carbocation. That we know the carbocation stability, the tertiary ones are most stable, the primary are least, and the secondary is kind of in the middle. So what do we have here? If that iodine were to leave, what kind of cation would we be forming? Secondary, right. So that iodide leaves, we form a secondary carbocation. Is that okay? Or is that not going to happen? It's okay. It's okay. All right? Secondary carbocations are okay. So that could happen. Okay. So then let's look at the nucleophile. Do we have a strong nucleophile here? Let's go back and look at our list of nucleophiles. Oh, we didn't talk about steric hindrance, but what happened to our list of nucleophiles? Here. Do we have a strong nucleophile? What? No, that's the leaving group. Yeah, it's a poor nucleophile, methanol. It's a neutral alcohol, neutral oxygen nucleophile is generally poor nucleophiles. So I just realized I messed up my counting here. So, oh no, I didn't. I just had 2 parts of the thing. Yeah. So we got nucleophile, substrate, leaving group, and solvent. All right. So the nucleophile here is going to favor SN1. What about the solvent? Do we have? It's the same thing. So it's a protic solvent, right? So it also favors SN1. So what's likely the mechanism of this reaction? SN1. Yeah. Most factors point to SN1. So if we were to draw the mechanism, then we draw an SN1 mechanism. The leaving group leaves to form a carbocation. Then the nucleophile comes in. And finally, we deprotonate it. So I want to show you another thing that sometimes comes up. In this particular reaction, we have a pretty clear sense of what's going on in here because we know we're in a methanol solution. But just so you know, another thing that's sometimes used in reactions is a B with electrons. That doesn't stand for boron. That stands for base. In many reactions, if there's different kinds of stuff floating around, we don't know specifically what is doing the deprotonating. So we just say B for some base. Something's acting as a base and grabbing a hydrogen. So if you're drawing a mechanism and you're not really sure specifically what is deprotonating something at the end, or even in the middle to give something, then you can always just use B for base and say some base that's in solution is deprotonating this thing. All right.
Will it work, like, for example, on a test? Because earlier I thought it was SN1 just by looking at the solvent, because you said that the leaving group doesn't really favor SN1 or SN2. Could I have just looked at that and automatically assumed?
I mean, I think it's a little dangerous because not always. It's not always going to work like that. So, for instance, on a primary substrate where you know you can't form a carbocation, that's going to go by an SN2 mechanism, even if everything else looks SN1-like, just because we know a primary carbocation isn't going to form. So it's still worth looking at the different factors. The opposite is probably more likely to be true, that if we see something that clearly points to an SN2 reaction, like one of these aprotic solvents, there's probably not any reason to use that except for that SN2, so that might be a really good clue that it's actually an SN2 reaction. So let's try one. Same question, but this time you're going to do it. Okay, I've got this cyclohexane, this disubstituted cyclohexane, and I'm going to add some NaSH nucleophile in acetone. What is the product, and can you draw the mechanism? So give it a try. Sodium hydrosulfide is what we would call that. I looked that one up. What is the what? The thing?
Like, is it like, what is it like CH? Like, what is acetone?
Acetone is yes. Product and mechanism. mechanism. All right, so this one, it's useful to think about first what the mechanism is, and then the product. Because we know the leaving group's going to be Br. Everybody sees that? And we know the nucleophile is SH minus. So we know the Br is going to substitute for the SH. The reason we need a mechanism here is because we now have a chiral starting material. Chiral reactant. And so if we have SN2, we're only going to form one particular stereoisomer. If we have SN1, we're going to make a mixture of stereoisomers. So what do you think about in this one? What mechanism are you going to go with? This one's SN2, and there's a number of reasons, a number of things that point to that. One is the very, very strong nucleophile, SH minus, extremely strong nucleophile. Second, we have an aprotic solvent, an acetone. The only thing that kind of goes against SN2 is the fact that this is a somewhat hindered substrate, that it's a little crowded in there because of the cyclohexane structure. But it's not too bad. If it had two tert-butyl groups pointing right down where we really couldn't access that carbon, that would be a bigger issue. But if you imagine the nucleophile here, SH minus, has to kind of come in here underneath the bromine. Yeah, there's some steric hindrance there, but it's not too bad. There's nothing really big under there. And then the bromine can leave. So this is a pretty easy mechanism. It's really just a one-step thing. And we just have to be careful about drawing the product properly, because we have inversion of configuration, which means the SH is now going to be going down because the bromine was up. So the SH will be on the equatorial position, going down. And that's SN2. So there's another example about, there's a question about the cumulative nature of our exams. So cyclohexane chair conformations was back in chapter 3, but we're still using those now in the context of the other things that we're doing. So we still have to keep all of that stuff in mind. All right. So please work through some homework so that you get a chance to practice that, deciding which kind of reaction that's going to happen. We're going to move on now and talk about two more reactions that also compete with the other two. So eventually we have to decide between 4 mechanisms what's most likely to dominate in any given situation. And these reactions are called elimination, or more specifically beta elimination, or even more specifically halogenation, when it's a halogen. And the reason these reactions also compete with SN1 and SN2 is because they happen with the same substrates. So alkyl halides that we've been talking about are also susceptible to these reactions. So here's what that looks like. We'll kind of do it all drawn out first, and then we'll look at how we at some more normal structures. So in general, this is how it works. You've got a hydrogen on one carbon, and you've got a halogen on the carbon next to it. We've been using X to indicate the halogen in general. As with the others, this is usually going to be Cl, Br, or I. That's going to act as a leaving group. And the reason this is called beta elimination, because it happens on the carbon next to the one with the leaving group. So the leaving group is over here. What happens is a base comes in, usually a strong negatively charged base, and deprotonates that hydrogen. But because that hydrogen is beta to a leaving group, meaning on a carbon next to a leaving group, instead of getting deprotonated and forming an anion, what happens is these electrons come down here and kick off the leaving group. Forming a double bond. So then the hydrogen's connected to the base, and then the X minus is the other byproduct. So it's essentially the reverse reaction of adding HX that we saw in chapter 5. Now, just like substitution, there are two ways to do this elimination reaction, two mechanisms by which it can proceed. One is called E1 and one is called E2, and they're analogous to SN1 and SN2. So this particular reaction that we just saw is called E2 because it all happens at once. The molecules come together, they do this reaction, this elimination, form the double bond, kick off the leaving group. The other version of it, if you have let's say something like this. If you have a tertiary carbon, again, you can form a carbocation or a secondary carbon. And then the base that is usually neutral or not very strong can deprotonate to form the double bond. So this one is actually like exactly the backwards reaction of addition of HX. I guess it's still not technically exactly the opposite, but basically the opposite. So we have something like that. And that's called E1. So, same idea. E2 is bimolecular, which means the two molecules come together at the same time and do the reaction. E1, unimolecular, which means the rate only depends on the formation of the carbocation, not on the base strength or anything like that. What? Yes. So two mechanisms, E1 and E2, analogous to SN1 and SN2. The 2 stands for bimolecular, meaning two molecules have to come together at the same time. And the rate determined, and that's the rate determining step. It's a one-step process. E1, the rate only depends on losing the leaving groups and forming the carbocation. Okay. Some other interesting things about elimination to keep in mind. Some more pages here.
So for E2, the rate is more determined by the strength of the base?
Well, by all of the stuff together, but yes. Strong bases tend to favor E2. We'll talk about which mechanism is favored in which conditions in a second. These elimination reactions are regioselective. So if we have something like this, notice we're using basically the same reagents as we did for substitution, so we'll have to talk about which one is favored. But in this case, there are two possible products. There's this one, and there's this one. Make that a little clearer. So we lose the leaving group, and then we can deprotonate at any carbon next to the carbon that has the leaving group. So there's two possible elimination products. The favored product is the more substituted alkene, so the one that has fewer hydrogens on it and more carbons. So that's the major product here. And then let's look at, like we did with SN1 and E1, or SN1 and SN2, E1 and E2. So you can probably guess a couple of these things. E1 forms a carbocation. So that's only going to happen in the same types of conditions as SN1. And we can think of it, this is sort of a general phrase, but it does work. SN1 and E1 go together. In fact, when you're doing these reactions, it's difficult or impossible to favor one or the other. The only way you would favor an SN1 over an E1 is if there was no possibility of even forming an elimination product, so no beta hydrogens at all. So these things are always in competition, and one's not really favored over the other. So anytime when you can form a stable or stable-ish, like a secondary carbocation with a weak base or nucleophile, you're going to favor SN1 and E1. And notice I said and. You're going to favor both of them. It's really hard or impossible to favor one of those over the other. So generally these products are going to have a mixture of both. So let's look at an example of that. In fact, that previous molecule is a good example. We're just going to change our nucleophile a little bit. So we have something like this that can easily form a carbocation. And we just dump it into some methanol. Methanol is a weak nucleophile. It's a weak base. It's a protic solvent. So it highly favors carbocation formation. So the first thing that's going to happen in this reaction is forming a carbocation. And then from that carbocation, there are, let's see, 1, 2, 3 different products that we could get. 1 substitution product and 2 elimination products. So the substitution product we've seen I'll try to color code these or something so we can keep them straight. The CH3OH could attach there, and we could end up with the substitution product. I'm also going to put on the arrow here just to be correct that we're losing H+. I didn't draw that separate step where it gets deprotonated. We're just assuming that for now so we can look at it. So that's our SN1 product. That's what we've been talking about before. The new products are the elimination products. Because methanol can also act as a base, a weak base, it can deprotonate one of the hydrogens here to make an E1 elimination product. Like that. We could also, this is getting crowded, deprotonate over here and make yet another elimination product. This one. So if we actually did this reaction physically, we would expect to see a mixture of all those three products. The bottom one here is the favored elimination product between those two. But between the elimination and the substitution, there isn't really a favored product in this particular reaction. We're going to talk a little bit about, I don't know if we'll get there today, but either today or Monday, about how we can control that and maybe favor one or the other. But in general, SN1 and E1 are always in this competition, and it's hard to specifically favor one over the other. Okay, so let's look at where we do have some better answers. Once my computer turns on again. Come on, come on, come on. There we go. Okay. SN2 versus E2 is a more useful comparison, often synthetically, because these are the products that are more directed and the ones that leave less up to chance and the ones that we want to target. We want to make this thing, we want to do this particular reaction. So we're going to look at some factors here. So one is steric hindrance favors elimination. In the previous section, we said steric hindrance makes SN2 hard because there's just not enough room for that nucleophile to get in there. But we didn't really talk about how that might work or why that might work, or how that, like, you could still have a situation where SN2 isn't really favored, or SN1 isn't really favored either. And in those cases, elimination is more favored. So if you have something like this, let's go back to our chair conformations. And let's say we have this thing from before. But now let's say we've got some big groups kind of hanging out here, a big terp-butyl group. On the equatorial position. So that's going to make it harder for that hydrogen to get, or for the nucleophile to get in there. Let's say also we have a pretty big base, or a nucleophile. So let's say instead of like sodium methoxide, what if we had potassium tert-butoxide, which is a common elimination base that looks like this. Remember the tert-butyl group? Well, if you put an oxygen on there, you have this pretty strong base, but it's also really big. So the chance that it's actually going to come up through all this junk and get into there to do the substitution reaction is low. It's just too crowded. So why would it do that when instead And actually, just for symmetry's sake, let's put another one over here so we don't have to worry about which side it's going to go on. So why would it try to get in there from all of that crowded room when instead it could just kind of come over here and grab the hydrogen to do the E2 elimination? Our chair conformation is going to look a little different now because we have a double bond in here. I'm going to draw it mostly the same anyway. So we're going to favor the elimination product there because we've got a crowded substrate and a big bulky base that takes up too much room to get in to do an SN2 reaction. And actually, yeah, let's look. So then the second major one we're going to look at to compare those two is nucleophiles versus base. So up to this point, we've really used those terms interchangeably. And we've said stronger bases mean stronger nucleophiles. And that's mostly true. But it's also true that some molecules act better as nucleophiles and other molecules really act better as bases. So strong bases, and when I say strong bases, I mean things like hydroxide and similar. So negatively charged small things like that. There are other elimination bases that are I don't think this book actually talks about them much. So we're going to stick to the oxide bases. But generally oxide bases like that, and then especially big ones, are going to favor elimination. Because of the strength of the base, they're more likely to deprotonate something than to go attach to something. The nucleophiles are generally bigger than oxygen, so negatively charged atoms that are bigger than oxygen. So things like sulfur nucleophiles, negatively charged sulfur, it's a very strong nucleophile. Negatively charged. Actually, you know what? I'm also going to add NH2 up here because that's going to be a strong base as well. The halides. So these weak bases, conjugate bases of of strong acids, like IBrCl. Then also the neutral nucleophiles like NH3 or other amines like that favor substitution. And then the last thing that we're going to look at low, moderate temperatures favor substitution. and high temperatures favor elimination. And that's true for the SN1 and E1 as well. So this is one way that you can sort of control between those, is through temperature. And the reason for that has to do with entropy. So elimination is more entropically favored, meaning you're making more disorder, more particles. We haven't talked about that much in this class, but that's maybe something you've looked at before. So elimination is favored when you have that high temperature, and substitution is favored at lower and more moderate temperatures. All right, so putting all of this stuff together, there's kind of a summary table in the book on page 215. That says, okay, what kinds of things can we do in these different types of substrates? So notice in the table that the first thing that you always look at is the substrate. So the whole table is organized by type of halide. Methyl, which is just CH3 with the halide, and then primary, secondary, and tertiary. And then what kinds of reactions can you have, and what's favored and what's in competition. All right, so notice also a couple of them are totally crossed out, meaning that those aren't going to happen. In the methyl one, elimination isn't even listed because there's only one carbon, so you can't make a double bond. But SN1 is not possible there because you're not going to form a methyl carbocation. It's just too unstable. Similarly, in the primary substrates, you're not going to do SN1 or E1. You're not going to form carbocation. Primary substrates don't form carbocation. Where it's trickiest is probably in the secondary, because those could potentially do all of them. So that's when we have to look at other stuff. So we'll skip that for a second. And then go on to the tertiary. And in the tertiary substrates, you're not going to form SN2 because it's just too much crowding. They're too sterically hindered. So you're always going to choose between elimination E2 or a mixture of SN1 E1. Notice also that in all the categories, SN1 and E1 are together, as we said. Those are always together, always in competition, and you usually can't tell one from the other. So those reactions are always a mess. If you're in SN1, E1 type conditions, you're going to form a big mixture of products. You're going to have to purify something. So as I said at the beginning, that's something more that we have to watch out for rather than something that we're trying to do. Usually if we're trying to do a reaction to make something, we want it to be either SN2 or E2, depending on what we want. All right, so let's jump back to the secondary category there and look at how we tell those apart. So if we have a secondary substrate, and we have a good nucleophile, a weak base, a good nucleophile like I-, we're looking at substitution. If we have a strong base, like hydroxide or other oxides, then we probably have E2 elimination. And if we have weak nucleophiles and polar protic solvents, then we're looking at a mixture of SN1. So as you work through the homework and practice problems on these, use this table. Have it right there. Look at it. Read through it. And then as you do practice, hopefully you can get away from the table and you can start having the table in your head and figuring it out that way.
So it's safely assumed we won't have this table.
You won't have the table. But here's what I would say. In your studying, yes, it's good to practice this with the practice problems, but the ultimate goal should be that you can actually derive this table from understanding the principles behind it. So if you really understand what the contribution of all these factors are, then you should be able to come up with this table on your own, because you can say, oh, I know a strong base is going to do this, it's going to favor elimination because it's going to want to deprotonate this thing, or I know that a tertiary substrate is not going to do SN2 because it's too crowded. So if you know the reasons behind things, that should help you get away from having to look something up at a table. It shouldn't just be memorization. It should be that you know what are the different effects for each that cause these things. All right, so that's chapter 7, and I'll see you
in lab.